Momentum 2. Impulse and forces. So acting on impulse, what does that mean? Well, force can be expressed in terms of momentum. How does that work? Well, force times the time that the force acts is a thing called impulse. And it doesn't have its own letter. We actually just use the letter for force and the letter for time, and Ft is impulse. Now, how does that relate to momentum? Well, Ft, the impulse, is equal to the change in momentum. How does that work? Well, first of all, the units for impulse are newtons from the force, seconds from the time, newton seconds. But you could also legitimately use the units for the change in momentum, which is kilograms meters per second. But most people would use newton seconds for impulse. Now, how does that relate? Well, we have this formula, Ft, that's our impulse, equals, that's our final momentum minus the initial momentum. Therefore, this bit here is equal to the change in momentum. So impulse, Ft, is equal to change in momentum. Now, the change in momentum, this bit here can be rearranged to look like this, which is F equals m multiplied by, because m is the common multiple, v minus u divided by t. Now we'd recognise that v minus u divided by t is actually equal to a. But we don't need to know that because we're interested in impulse. And so this t and this t can come across here and give us the momentum, or the change in momentum. Okay, so the change in momentum divided by time equals force. That's how momentum is related to force. Okay, if you have the greater the force in the shorter the period of time, the greater the change in momentum. Yeah. So on our information sheet, you're given P equals m times v, our momentum formula. You're also given F net. That just means the sum of all forces equals the change in momentum divided by t, and then the change in momentum is expanded to m times v minus u, which you could then expand another step further, saying mv minus mu divided by t. You also have F net equals ma. Now these are all related to each other because momentum and time and force and impulse are all related to each other. So momentum is there, mass is there, velocity is there, force is in newtons, change in momentum is there, time is there and there, change in momentum is also over here, and force is always down here, which is equal to ma. So what, you ask? Well, if we've got this, which is a variation of what we were just seeing, we've got F net equals momentum delta v, this case, just to confuse you, where m times delta v is expanded into v minus u, final velocity minus initial velocity, over the change in time. And this change in time is the time period that this velocity change took place. So why is that important? Well, if you are going through a change in velocity, you want this change in velocity to apply over a longer period of time, because then this force is reduced. Now in sports, some of the situations that occurs in, for example, when you are landing on the ground, you bend your knees, and by bending your knees you increase this time over which a change in velocity occurs, because your mass stays the same, and therefore you decrease the force that your body is experiencing on landing. You move your hands back when you catch a ball. Catching a cricket ball or any hard ball, you try and move your hands with the ball, and that increases the delta t and decreases the force. Wearing gloves in baseball and softball are all about decreasing the amount of force you experience, and that's by increasing the delta t. And wearing good shoes. Although some people are now running barefoot, wearing good shoes makes good sense, because every step or every running step, your foot has to decelerate and then accelerate, and by changing this, making this delta v long, your ankle and your bones and your feet and your legs will experience a smaller amount of F. And more importantly, wearing a helmet, be it a push bike or a motorbike helmet, it's all about, if you go through a collision, you want to have this change in velocity occur over the longest period of time. That's why you have all this cushioning around your head, and because the head will then experience a less net force. Now, force time graphs you need to be able to interpret, because we're interested in the impulse, remembering that impulse is related to momentum. And so the impulse is equal to the area under a force time graph. So here's a force time graph, and the impulse is this area here under there, and we should be able to work that out fairly straightforward. Okay, what they've done here is they recognize that if we did a rectangle of this shape, okay, this triangle represents half of this rectangle. Fairly clever. Some people would have divided it in two and times it by 2, but as long as you get the right answer, you don't mind how you do it. Now notice that the units are Newton seconds. What about this one? Here's a force graph, and again it's the area under that graph that will give us the impulse, and 125 Newton seconds. So now you should be able to do questions 5 and 6 that are given to you. And in the next video we're going to look at conservation of linear momentum, looking at explosions. See ya.